It worked 10 minutes ago? Ah, here it is. Okay. Okay, thanks all for joining. I'm going to tell something about Apache Arrow. I'm going to try both explain Apache Arrow for those that are not yet too familiar, as well as show some newer developments for people already knowing Apache Arrow. Quickly about myself, I'm an open source developer, almost full-time maintainer of pandas. I'm also involved in the geospatial stack. And so I'm mostly working nowadays at Apache Arrow, more specifically the Python bindings PyArrow. And I'm doing that at Voltron Data. So we are a company building Arrow native data analytics. So let's get started with Apache Arrow. So what is Apache Arrow? It's many things, but so at its core, like the main thing is that it has it specifies or a standard how to represent columnar data or tabular data in memory. That's the core specification. There are some additional specifications around that. And then you have many languages, many implementations in various languages that implement those specifications. And so you can, at least in the past, you had various, for example, various dataframe libraries in R, in Python, databases, Spark, all having their own custom memory, in-memory formats. And so if you want to move data around from one system to another, you constantly have to copy and convert, serialization, deserialization costs. And the idea about Apache Arrow is that if you have this common standardized memory layout, that either those data frame libraries or databases just use natively themselves or have like a very efficient conversion for, then you can much more easily and cheaply move data around from between different systems. And you can also share implementations. For example, a Parquet reader, it's much more easily to share such implementations. It's not only meant for moving data around. The memory format is also meant to be an efficient in-memory format for actual processing. So it's, we call it the columnar format. So it's columnar. Each column, like the data of each column is in a contiguous buffer. So that's in contrast to the traditional databases that were typically row-based, where you have data of one row of potentially different data types together, while if you have each column together, that's more suited for efficient vectorization and efficient operations. This is not something like new. Pandas already did that from the start, for example, but it's like the core, one of the core ideas of the format that makes it efficient. As I already mentioned, that's really the base of everything in the Arrow ecosystem. A few more details about the format. So it's as expected for a standard tabular data format. It supports a wide variety of types. In comparison to the more traditional, at least for the Python world, array library types that we know, for example, NumPy, Arrow also supports variable size or variable length strings, or binary data, nested types, for example, where every element in your column is a list or array or a struct. It also, in contrast with typical array libraries, has support for missing values for all data types. And it does, Arrow specifically does that by defining bitmap, so basically a separate mask, keeping track of where you have valid or missing values. And I want to point out that it's nowadays actually really has become the really standard, and this figure is a very old figure that was, I think, it's 6 or 7 years old, but made in the beginning when the Arrow project was started. And at the time when the figure was created, this was really the vision of Arrow. That's what they wanted to achieve. And yeah, nowadays it's actually reality. I don't know I'm not super familiar with all the names on this figure, but you could certainly make a similar one with pandas, R, Spark, Snowflake, BigQuery, ClickHouse. They all use Arrow to interchange data. This is a bit an overview. So in the middle, we have the columnar format. There are some additional specifications on top of this format. So the one that has been there from the start also is the IPC, interprocess communication. So you have something in memory, but now you want to send it to a different process, send it over the network. And so the IPC format is a very shallow, efficient serialization format, but specialized for Arrow data. So that has been there from the start. And later in the talk, I will focus a bit more on on two of the other ones. On top of that, you have lots of implementations in various languages. Most of them, at least all of them, all implement at least the core memory layout and the serialization format. Depending on each implementation, you will also have a different level of how much tools that they provide and to actually compute things on Arrow data. And so if you look at from a Python point of view, so there are some of the Arrow libraries that you can actually use to not just move data around, but to do actual computations. So you have the Arrow C++ implementation with the PyArrow bindings, where we have a compute engine, which is called Acero. The Arrow Rust implementation, you have the data fusion project. It's in Rust, but you have Python bindings. They have a full query engine. You also have another Arrow implementation in Rust on which Polars is based. So Polars itself is not an Arrow project, but it's built on top of an Arrow implementation. And so various implementations of Arrow are already being used nowadays to to expand the data frame ecosystem in Python. And for example, also IBIS can then interface with all those three. IBIS is a Python library that gives a data frame interface but has different backends, and they can also use various backends based on Arrow. Apart from libraries that are really from the Arrow projects, there are also various newer systems or computational systems that are don't necessarily use Arrow directly, but are fully or partly compatible with Arrow. For example, you have the Rapids project for GPUs. On the QDF, they use Arrow memory internally. DuckDB is not related to Arrow, but it's very much compatible with Arrow. So if you get data in or out DuckDB, they will use Arrow. Velox, similarly, it's a relatively recently open source project from Facebook. So basically the new compute engine from Facebook. They are not using Arrow directly, but they are compatible, so you can easily, and because they all use Arrow, you can, if you have your tooling and you ensure that your data is in Arrow compatible format, you can very easily integrate all those different tools in your workflows because of this common memory format. I'm myself most familiar with the Python bindings, or at least the PyArrow, so the Python bindings to Arrow C++. And this package provides a whole set of building blocks that are being used throughout the ecosystem, both for just implementing the specification, using it for all the serialization, moving data over the network, also accessing data on file system, different file formats. And so PyArrow is certainly in the early years was mostly used for reading Parquet files. Nowadays it can do a lot more, but it's still a major use case. Reading data sets, and so also has a compute module with a whole bunch of computational kernels. And this is already now being used widely in the PyData ecosystem. And for example, Dask is using the data access to read files. Dask is using that a lot. And I learned at the conference that Dask also started to use the IPC serialization in their distributed shuffle implementation to optimize that. And another example of where Arrow is being used as a compute engine as well, improving the data frames, is pandas. So on Monday, Patrick explained or showed a bit how pandas is starting to use Arrow under the hood. And yeah, you can find more details in that talk. Now, I want to, for the rest of the talk, go a bit more in detail on some of those aspects and how those things are working. So I've mentioned that all those different libraries, they can easily share data. But so how that exactly works is based on one of the other specification elements that are mentioned here below. And so first I want to focus on this one, the C data interface. So as an example, polars and Arrow. So I created the small polars data frame. Polars has a method to Arrow to convert it to an Arrow table. We could further convert it, for example, to pandas data frame or to some other library. But in this case, so the data of those both objects is actually the same data. So this conversion is like zero copy fast conversion. And although both are Python libraries, the one is implemented in Rust, and so the actual data is under the hood is a Rust object. PyArrow under the hood is a C++ object, and they are pointing to the same data. That might seem trivial, but that's really only possible because of the standardization of the format by Arrow, and also by a specification that they can actually share pointers between those independent runtimes without that they need to be aware of each other. So polars, of course, imported PyArrow under the hood to create this object, but it's not that polars needs to know how the C++ object is laid out to create it. It doesn't need to compile against the Arrow C++ project. And so how that works is through one of the specifications of the Arrow project, which is called the C interface. So it's meant for zero copy sharing of data between independent libraries, between languages within the same process so that they can share actual data. It's based on a few small C definitions. So if you have a language that can interface with a foreign function interface like CFFI, then you can work with this. And so it allows to integrate with the Arrow format without necessarily using the Arrow software or without necessarily knowing the other library that would like to consume your data. It's used by, so I gave the example of polars, but also if you move data from DuckDB to pandas or Python in general, it's being used. For data fusion, the same, and a bunch of other libraries are already using it as well. For example, to share data between Python and R, it's the same story. How does this work? So that's one example of such a C definition. So it's a struct. And in the end, it's really just pointing to some buffers. Like these are, here you have pointers to buffers, and that is being shared with some metadata to know how to interpret those buffers. And some additional tooling to manage lifetime and things like that. There is an array, there's also a schema, so the data type is shared separately, and you have a streaming version of it as well. One example that's near to my heart that I want to show is GDAL. GDAL is most widely used library for reading and writing spatial data. Basically, every geospatial software that does some I/O uses GDAL. It's a C++ library. How does it work? Typically, if you want to use it from Python, so I'm also maintain one of the Python bindings for GDAL. GDAL loads data from some file format into its own data model, and then it has an API that we can call from Python, where we get the data row by row. But that's, yeah, has a lot of overhead. It's also a lot of work to implement this if you want to get the data into a tabular format. And so we can improve this by using Arrow there. And that's something that has been implemented in the latest version of GDAL. So they now have a way that that GDAL directly creates Arrow data, and as the Python library, we can directly receive the data as Arrow instead of receiving it row by row and having to build up the data frame ourselves. GDAL can then also even optimize it depending on the file that they are reading, how to construct this, the Arrow data. I'm going to skip this a little bit, but so it's also using the CData interface so that anyone who implements can consume that, can directly integrate with GDAL, and it gives a very nice speed up, apart from just being much easier to use as a consuming library. It's not always easy to implement the CData interface. So, for example, GDAL did that fully themselves. Like the maintainer did a very nice effort there. But to make that easier, one project that I want to mention that a colleague of mine has worked on a lot is NanoArrow, and it wants to give an easier to integrate some helper functions to work with this CData interface. So it's a small C library that you can vendor, and so that you don't have to necessarily have the Arrow C++ library, which is a very large library, lots of features, so that you don't necessarily have to use that big library as a compile time dependency, but just can vendor NanoArrow. And so, with the goal of making it easier to consume, produce data in this format. The second thing I want to show that is relatively new in the Arrow ecosystem, and that also builds on top of the CData interface, is what is called the Arrow Database Connectivity, or ADBC. And so this is about getting data in our databases, and so something that is used very often are protocols are like interface like JDBC or DBC. In Python, we could also, I mentioned the PythonDB API 2.0. But essentially what happens here is that these are generic interfaces. So as a user, you can use those generic interfaces. Then you have some driver that translates that your query to something database specific, gets the data out of the driver, and then returns those data to the user. The main problem with those interfaces are that at the moment they are all row-oriented. ODBC can do some columnar-oriented data as well, but it's not very compatible with Arrow, so I'm going to leave that aside. And so, you get data row by row, while maybe even your database could be columnar, and you want columnar data in the end, but so you have to pay the conversion cost twice to use those interfaces. And so that's why ADBC was introduced. And so the idea is very similar. It's also database agnostic interface, so that you can use it with any database behind the scenes. You again have a driver that translates your query to a database. Either you have a database that is Arrow native and can just directly return Arrow data, or you could have a driver, for example, for PostgreSQL that will convert inside the driver already, so you don't have to do that yourself. Convert the row-oriented data to columnar Arrow data and return that to the user. So the goal of ADBC is to have a single API to get Arrow data in and out of databases. So that's Arrow native. It's also using the C data interface to not be specific to a certain implementation of Arrow. It's vendor agnostic or database agnostic. And so, yeah, defines a common client API interface that various databases, or you can have drivers for various databases. And it's focused on not necessarily to replace those existing interfaces, but focused on cases where you want columnar data access. Small example how it works in Python. So there are already some drivers, very initial versions. They don't necessarily implement everything. There are some available, for example, for SQLite and PostgreSQL. And they provide a very similar API as other Python database libraries. So you also create a connection, a cursor, you execute a query. But instead of using the typical fetch one, fetch all methods, there is a fetch arrow table, and you get the data at once. So that's, you get columnar data. We have initial versions, but they're very much, so it's only from the start of this year that this has been adopted by the Arrow community. So it's very much early state of those drivers. But just a small example for the existing SQLite driver. So I use pandas to write a data frame to a SQLite file. I read it with the current version, the current implementation of pandas, or I can read it with the SQLite driver. And what you see here is mostly avoiding the overhead of that pandas does this row by row, retrieving row by row and building up the data frame in Python. To end, I want to mention one more thing about specifications, one that is not from Arrow itself, but very much related. So for example, in the case of ADBC, you still specify a SQL query to indicate to the underlying database or other data provider what data you want to retrieve. But yeah, SQL has many advantages, being many people knowing it, being very widely supported. But so Substrait is another project that tries to be a universal standard for representing relational operations. And so the idea is that Arrow is the standard for the data that you retrieve, that you get, while Substrait is the standard to specify which data you want. And the idea is that, currently you can have all kinds of interfaces, like whether you want to use Python or R, or which package in Python, which package in R, various possible interfaces. You also have lots of query engines, and currently, for example, IBIS has backends for 15 different backends, I think, while in principle, so Arrow already improves how data moves between those different layers, and Substrait could also improve how you pass the information, like what do I want to compute. That's a very brief primer on this separate specification. So, thanks for your attention.
Thank you very much for your talk. Also, we have quite some questions, and I will just start by popularity of those questions. And the first question we have is, so pandas and Spark use Arrow to exchange data, but how does PyArrow serialize data itself?
For example, the serialization is used to move data from Spark to pandas, and the serialization format is essentially using exactly the same format as the in-memory data, like how the data is laid out in memory, and but putting some metadata around it, and in in a single buffer. But by using mostly exactly the same layout as the in-memory data, that makes it efficient with not that much serialization, deserialization costs.
Oh, thank you. I think this covers the question as far as I understood, but I'm sure you will also happy to answer questions if it was not precise enough or you want more detail.
Sure.
The next question is, when I use pandas or Spark, does it automatically use Arrow in the background, or do I need to enable this somehow?
For Spark, I'm not super aware. I know that it depends on the version and that they are moving to columnar data in more recent versions, but I don't know the details there. For pandas, it's currently something optional. We don't use it by default. We use it by default, for example, for reading parquet data, but we don't use it by default as a memory representation. There is a dtype backend keyword in several of the I/O methods that you can specify to actually use Arrow memory for every column. But yeah, if you want to know more details, there are some examples in the slides that I mentioned from Monday.
Okay, thank you. Then let me check the next question. How did Arrow manage to be adopted by so many libraries? Usually when you invent a new standard to unify all of them, you end up with a new competing standard.
Yeah, that's a good question. I think it probably shows that it really filled the need and that it provides a lot of value. I suppose it's mostly that.
So you generally think there's some need for unifying concepts or unifying the zoo of tools available? Yeah,
it's certainly from the start. I wasn't there fully from the beginning in the Arrow project, but it certainly directly provided at quite some concrete use cases where it provided a lot of value. For example, the example of the Spark and Pandas, what was mentioned before, moving data from PySpark to Python, if you have like a user-defined function, that was really slow some years ago because they had a custom way of sending the data from the JVM to Python and back. While many years ago, when they enabled using Arrow as the way to send data around, they really improved user-defined function in PySpark with a huge amount in performance-wise. So directly from the start, there are some very concrete benefits, and I think that certainly helped with, paving the way for broader
So
adoption.
Coming from the use case, you would say it's really a benefit to show the value, and from there on, it just went its way.
Yeah.
Okay. Yes, I think we have time for one or two more questions, maybe. Maybe I'll pick this one. How good is the ADBC currently, and where are the pitfalls right now?
Well, I think the SQLite is rather feature complete. It's certainly not optimized. It's more meant for a proto showcase. The PostgreSQL driver is certainly not fully not fully feature complete. It only supports a limited number of data types. I don't know them by heart. But yeah, it's only released a few months ago, the initial versions. So that's very much work in progress. So I wouldn't say that those drivers are currently they're far from production ready, but it's certainly the goal to improve those drivers, and also that the hope is that database implementations will start to provide drivers for their database based on this protocol. Just as all the other systems are adopting Arrow, we hope that this can happen here as well.
Thank you very much for your answers. Also, thank you very much for your questions. Unfortunately, we don't have any more time, so if there's any more questions, just address Joris, and let's thank him one more time for his talk.